Okay, so let's start our lecture today. So I'm going to try to solve for the why the sum of the so why this converge uniformly on the image of this curve gamma. So um, okay. So basically, we want to show is that so I think so for each z, right? So the absolute convergence gives the conditional convergence, right? So so we don't need to show that the limit exists. So we just need to show that it's converging. It's a uniform convergence on this image set. So so maybe I need to erase something. So let me just copy it here. So wait. So this is equal to what? So this is equal to so what we so what do we show? So we show that what we show is that the modulus of the line integral over gamma of fz dz is less than or equal to, so this is minus, right? So minus the line integral over gamma of snz dz and then taking the modulus is less than or equal to the supremum of the over gamma of the modulus of f minus Sn, right? Supremum over gamma of modulus of f minus Sn and then this one times the length of gamma, right? Okay, so let's see whether it's recorded. Okay, nice. So so I think I just do I need this one? So I think they converge locally uniformly. Maybe I think I need this one. So why is it true? Yeah, so y is true. I don't think I need this one. Okay. So this implies that this one goes to 0. Okay, yeah, so this is a consequence. So yeah, so let's just do this one. So let's just do this one. So 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 uniform convergence implies that the limit exists, right? The limit goes to infinity n from 1 to n of the this part 1 over omega plus z over omega squared exists, right? So so now I want to show that this converge uniformly on this image set, right? So y is converging uniformly. So I think maybe I must relate this to some modulus. So for every v, right? It is for every v. Sorry, z in this image, right? Okay. So for every z in this image of gamma, so so let's yeah. So yeah, of course it is. And the image is just the zeta, right? So which is equal to, I think it's by definition the zeta, right? Yeah, so we define it to be the zeta. Okay, so the point with limit. So now what I have is that, so let's take the some difference. So then we have that because I want to use the some absolute value, right? So I want to just try to see if I can use some triangle equality. So so then I have that the so let's call this Sn, right? So let's call this Sn. I think I called this Sn before, right? So then Sn minus zeta z, Sn(z) minus zeta z. Shoot. Wait. Yeah, so it looks like, okay, so yeah, so let me, which is equal to Okay, so this is equal to what? Oh, so this is equal to, okay. So this is the first n-sum, right? Right. So this is the first n-sum of this guy. And then so this is what? So this is like the like from 1 to infinity, right? So this is like the limit. So yes, so this is the limit. So this whole thing is a number, right? So so this guy so the things inside should just equal to the should just equal to the so which I claim, so I haven't shown it yet. So so maybe I'll use so okay, so I want to show, yeah, so let me do this. So I want to show you that yeah, I think this is true, right? So I think, so basically this is equal to the modulus of limit as let's see, n goes to infinity. Sorry, I can't use this n. So maybe let me use this n. And then I start at n, right? Sorry, I start at n plus 1, right? Maybe I use the letter m. Okay, so from n plus 1 to m, and then I have is that of this guy of someone here. Yeah, basically like you just switch this one, and then let's see why. So so because basically so here, so this one is equal to so yeah, so this guy is equal to the modulus of yeah, so here you have the limit from, so this is the limit, right? Minus a number, right? Yes. So this is a number. Let's say this is minus a number. Let's say k, right? So so let's call this k. Okay, so so yeah, so this is a limit minus a number, so it should be equal to yeah, so it should be equal to the limit of let's see, so maybe I use another letter m. M goes to infinity of this limit, right? So this is the limit that this is taking here of. So the limit of the partial sum minus this k, right? Yeah. So so what's it called? So maybe let me write it here. M goes to infinity of this one, m from 1 to m, right? So this is like one term here and one term here, and then this is equal to the limit of just the limit term here minus this term k here, right? And then this is exactly equal to the limit of just this term, right? Because for the first, after this m is bigger than this n, they are all the same, right? So we don't need to bother about, because the limit is basically, it's been defined for, so basically when this m is very large, these two behave the same, right? So basically, so this is true, right? So this is true. So so let me. Okay, so maybe I want to check it more carefully because I don't want to. So let me try to take it more carefully. So this one is sum from so we are taking the limit minus k. So for any so y is equal to so n from 1 to m of just so here, right? So So basically that C be the limit. Right, so let's see this limit. And then okay, yeah, I think I'll just leave this one as an exercise to show this one. Yeah, I'll just leave it as an exercise. So yeah, so this one is equal to this guy, and then so what we have is that we have so we know that so this is less than equal to the limit as m goes to infinity of the sum of the m plus 1 to m of the modulus, right? This is the triangle equality. Because we know that for each term it is less than equal to this sum, right? And then when we take the limit, it's less than equal to this limit. So so what happened here? So we know that this guy converges uniformly on this compact set, right? So so basically there is some uniformness on the absolute value, right? And then this wait. So there is some uniform. So this uniform does not mean the. Okay, I was little bit messed up with the absolute and the uniform. I was thinking, it has already have absolute value, but why it has some absolute convergence, but it's not absolute convergence, but it's a uniform convergence. So never mind. So never mind. So here we have the uniform convergence, right? So we have uniform convergence of this guy on this compact set, right? So this is what we have. So there is some uniformness for the absolute value, right? For the absolute value of the of this of the absolute value, and then And then and then so this means what? So this means that there is probably I'm guessing is that there might be some absolute value. There is some uniformness on this one, right? Yes, so there might be some uniformness on this one. And then can we use the uniformness on this one to sort of balance this one uniformly, right? So this is my approach. Yeah, this is my approach. So let's see. So so what do I need to show here? So we know that. So by the uniform convergence of the so that's our argument here. So by the uniform convergence of this guy, so maybe I need a ladder for the limit, right? So let me see this. So that I think I need a ladder here. So what ladder do I want to use for this uniform limit of the absolute value? So let me think. Yes, yeah. So what value do I want to use here? So maybe I'll just use AZ to be equal to the limit, right? Yeah. So here a little bit I built in the notation here. So let me just say that this is equal to the limit here. Okay. So the uniform convergence of the so by the uniform convergence of so by the uniform convergence, so we know that, so we have the supremum of so we know that the supremum taken over gamma of maybe I'll use this one. So Z in this image of gamma of the over the modulus of of the difference between these two. So maybe I'll use the letter n. So n from 1 to capital N of the modulus 1 over z minus omega minus, it should be plus 1 over omega plus z over omega squared. So it should be minus, right? Az it goes to 0, right? So and then so what we have is that so what we have is that yeah, so by the argument we did before, right? Yeah, so argument before shows that yeah, so since we have that the modulus of n from 1 to n of this modulus so this AV literally is just the sum over all the sums, right? So which is equal to just this limit, right? So from n plus 1 shoot. Yeah, I was yeah, I need to be a little bit careful here. So what really I mean by yeah, so this should be equal to oh yeah, here, right? So it should be equal to the limit as yeah, same argument, m goes to infinity of sum of n plus 1 of m, but with the modulus here, right? So 1 minus z minus yeah, omega plus 1 over omega plus z over omega squared, right? Start from n plus 1 and then go all the way to infinity, right? So therefore we know that this guy goes to 0, right? Right, so this guy goes to 0. So therefore what we have is that yeah, yeah, so this guy goes to 0. This guy goes to 0 implies wait, I think maybe I need some argument. Let's see. So yeah. Sorry, I think I need to be a little bit careful here by what I mean by this goes to 0. So yeah, so the supremum, yeah. So what I mean is that so the supremum of z in this image of gamma of this guy, limit m goes to infinity of summation m from n plus 1. Shoot, I think I made a big mistake here. So yeah, sorry, this omega should be omega n. Yeah, otherwise this is not true. So yeah, sorry. So it should be omega n here. Yeah, otherwise this does not make any sense. So this should be n equal to n plus 1, right? Sorry. And then we have that. So m goes to infinity of so n from n plus 1 to m of the modulus. So here is the modulus of this guy minus omega n plus 1 over omega n plus z over omega n squared. This one goes to 0. Goes to 0 as n goes to 0. Yes. Yes. So yeah, I think we can now find an upper bound for this guy, right? So yeah, sorry, I think it should be the s of capital N, right? So sum from 1 to capital N here. So so how can I find an upper bound for this guy? So how can I find an upper bound? So okay, so so yeah. I think these two are the same, right? Because this limit, right? So this limit. Yeah, so because this is always positive, right? Yeah, this is always non-negative, right? So therefore, I can erase the absolute value, right? Wait, the limit of yeah, okay, I can just erase the absolute value because this is always positive, right? Wait, can it be equal to 0 all the time? yeah, I don't think it can be 0. So otherwise, yeah, it is it is just the negativity just implies this one. Yeah. Oh, okay, okay. So yeah. So and then so supremum of just this guy, right, goes to 0. So okay, so then so this means what? So this means that yeah, so this means that when n is large, right? So this guy must be very small, right? So so yeah, so for n large, we can pick this is less than epsilon, right? So yeah, so for let's say for a large, this is less than epsilon. So therefore, yeah, so therefore this goes to 0, right? This goes to 0 when this n goes to infinity, right? So this goes to 0 as n goes to infinity. And then since this z, so basically it holds for every z, right? Because for each z, this is this guy must be less than or equal to the supremum of this guy, right? So therefore, since this holds for every z, so therefore it goes to 0 uniformly, right? So this argument doesn't depend on any z, right? Right? Because for each z, it is for each z, this guy is less than or equal to the supremum of this one. So maybe let me write it down. So so for each z in this image of gamma, we have that So for each z in image of gamma, we have that the modulus of SNZ minus zeta z is less than equal to the limit of m goes to infinity of sum from sum of n equal to a equal to n plus 1 to m of the modulus of the sum 1 over z minus omega n plus 1 over omega n plus z over omega n squared. So which is less than equal to the supremum of z in image of gamma of the so which is less than equal to the supremum of z in the image of gamma of the set limit m goes to infinity of summation n from n plus 1 to m of the modulus of the 1 over z minus omega n plus 1 over omega n plus z over omega n squared. So yeah, so this is just the because this z is in this image of gamma, right? So therefore this one is less. So this one is less than equal to the supremum of z in this image gamma of this guy, right? So therefore, what we have is that we have and also since the supremum of z in image of gamma of this one so goes to 0. As n goes to infinity, right? So we have that. So for any epsilon bigger than 0, there is let's say n tilde in this z positive integers such that when this n is bigger than or equal to this n tilde, would imply so the supremum of this guy, right? Supremum of z in this image of gamma of this limit n from n plus 1 to m of the modulus. Yeah, so here maybe I should equal to n of the modulus of 1 over z minus omega n plus 1 over omega n plus z over omega n squared. Sorry, squared here. So this whole thing is less than epsilon, right? Because this guy is always positive, right? So this is not negative. Sorry. So I can just freely erase the modulus here. So and then so this implies that. So we know that. So this one, which is that, right? It's the same thing. So it's the same thing. So this is less than epsilon. So this implies that. So this implies that this modulus of Sn(z) minus zeta z is less than epsilon for this for this n large, right? So for this n bigger than equal to the n tilde. Okay, and also this z is arbitrary, right? So so z is arbitrary. So this implies that we get the uniform convergence, right? Oh, we have already showed the uniform convergence. Yes. So yeah, so Sn(z) converged uniformly. So converges uniformly to this zeta z on this set, right? Okay, so So this implies that if you take the supremum of this z in this image of gamma, sorry, I should really say this z in this image of gamma of this guy. Wait, what is Fz though? I think this Fz is just zeta z, right? Yes, sorry, I forgot. Yeah, so I think initially I was doing something like, yeah, I was using like I was copying from the ChatGPT and then I think he used the letter Fz, but in this case, in our scenario, right? So this F is really the zeta z, and then this S and z basically is just the partial sums of this guy, right? So yeah, so at least for now we show that so we show that, so we show what we show, right? So we show that this this S and Z converge uniformly to this zeta Z on this this compact set, right? So we show this one. So okay, so oh. Okay, so maybe next time I'll just pick it up from here. I'll try to recall what I. So I think what I did last time is yeah. So I'll just try to recall from here, right? And then we shall move on. Okay. All right. Thanks for watching.